So tonight we have with us a very special speaker. He's got quite a long list of credentials here, so I might have to cheat with the paper. But he's the founder and VP of Engineering and Operations at Aerospike. He's got 20 plus years of experience. Over a dozen patents in database, internet, and mobile technologies. His former roles, he was the chief architect for IBM's DB2 internet products. He also worked at Yahoo's mobile products, where he had the global responsibility for their mobile products used by tens of millions of people. Please welcome Srinivasan.
Thanks, Eric, for that great intro. Can you hear me? The mic is working?
I don't know.
Is it any better now? Can you hear me? Yes. Better now? Oops. Okay. Yes, I can hear myself. So I thought instead of first of all, my other co-founder from Aerospike, Brian Bukowski, is also here today. So a couple of others, Monica and Dino, are also here from Aerospike. I thought I'd start the talk with the demo. I mean, some of you who've been here before have seen me kind of go and stop servers and start servers. I just want to tell you what is going on here. So there's a 4-node cluster running in Mountain View in our data center. And each of these nodes, the transactions for each of those nodes is shown on these graphs. And on the first graph on the top, on the left, is the total transactions per node. As you can see, with 4 servers, we can run 1 million transactions per second on this cluster. That is the max throughput. After which I reduce the throughput to about 400,000, which is kind of not normally, you want to give a little gap. If you're an ops person, you know that you don't want to run fully. So that's what I did. If you notice, look at the response times, it's well under 1 millisecond, typically 0.2, 0.3 milliseconds. So what I want to do now is ask the audience which server they want to kill. 3? Okay. So I don't know why it's always 3. So I'm going to kill server 3. So what you should see is the system's going to try and keep the transactions per second for the cluster at the same level. Let me remove that little window there. You can see what's going on. So what you see when the server goes down is that essentially each of the remaining servers, 3 has gone down to 0. The remaining server should pick up the slack and go to 133 kbps here per node. So you can still keep the transactions per second up. So if you look at the response time, you saw a little spike. There were a bunch of timeouts potentially for requests which were in flight at that point. All of those response times are measured from the client. The client's a Java client. Servers, of course, as one of the answers in the quiz, written in C. So anyway, so that's what we do in terms of how we run our system. We basically run 24/7 and so on. So let me get into the actual presentation. I'm going to switch computers right now. Except that it does something. Just switch. Thank you. Okay, great. So essentially what Aerospike does is we produce a predictable, we're a key value store with predictable performance in real time. Talk a little bit more about where we are in the database landscape. Our goal is to be in the big data transaction space. On the left half of this chart, you see the traditional structured databases. On the top half are the transaction databases, mission critical and operational databases that you see running 24/7. And then on the bottom are the analysis databases. So everybody should be knowing about Hadoop as being a big data kind of area. What we are actually focused on is real-time transactions at very high throughput and very low latency. So think of it as basically a new database for real-time access.
Did you say transactions will be asset?
Yes, going forward. I will kind of delineate where we are today, where we expect to go. Yes, so that's our target. Okay, so the key thing about Aerospike is we are fast. Essentially, we can do, we showed here about 250,000 transactions on these free commodity nodes. We can do, there's a blog about how we can run 1 million transactions per second on a $5,000 node and so on. The other thing we do is very important, is we are able to, of course, deal with lots of writes and reads. Otherwise, the problem is not as hard. Essentially, you're able to do high write load and high read load at the same time with sub-millisecond latency. Okay, that's the fast part. The scaling is really important because it is one of the main reasons many customers actually choose us, is because we can size the system in such a way that when you just talk to us for an hour or even less, we can tell you exactly what is your hardware requirements going to be, what the system structure is going to be for your deployments, not just for today, but over a growth period. And that's really important that we scale linearly for you to be able to do that. Of course, the other claim to fame we have, I just showed you in the demo, we don't fail as a service. As a product, we have been in production for over 2 years now. And we have pretty much kept all our customers up 100% of the time. And the way we do that is by clustering. I showed you, one node goes down, we're able to pick it up. And even in large clusters, even with more than one node going down, you actually have, the way we do our algorithms, you have access to virtually all the data still. And there's a birthday paradox there in all about data. So that's kind of what we do at the high level as a product. A little bit about the company and customers. So the obligatory team slide. So we basically people who have a lot of experience in the database, performance, internet, and networking. A couple of our advisors have been key contributors or pioneers, I would say, in the relational database field. Don Adderley from IBM and Roger Sipple, founder of Informix, who ran it for 10 years or so. And myself have a database background. Brian, my co-founder, is the networking expert from the early days of networking. He worked at all the pioneering networking companies and then migrated to databases over time. Russ is a high-performance expert. He's the founder of Alchemy DB, which is been merged into Aerospike. And he actually built an interesting, I'll talk more about it, querying and indexing platform, which we are now working on Aerospike. Just a little bit about our customers. AppNexus was our first customer, one of our largest. We also have big customers, in the data space, Exalate and BlueKai. AppNexus does about 30 billion impressions a day. Exalate has about 16 terabytes of data across 4 data centers, running 24/7. BlueKai does a couple of trillion impressions, transactions, whatever, in the data space. I don't know exactly what they call it per month. We also have some of the largest video advertising platform, Rightro, We kind of have a global set of customers. PubMatic is a very interesting company which deals with publisher side, on the advertising side, they do publisher-based stuff. They actually the competitor of AdMel, which got bought by Google at some point last year. So we basically, all of these customers, one thing is common is they run their mission-critical, real-time systems using Aerospike, and they need to run 24/7. If you're down for 5 minutes, they're losing money. The usual, they want to sleep at night knowing that the system is up and running. I'm just going to go a little bit into the technical aspects of the talk, a lot actually into that. First on the system architecture. First a little bit about the challenges that we have. Right? There are a couple of key areas of challenges that we wanted to focus on when we founded the company. One set is on the application side. We wanted to enable very high throughput systems, which were also had low latency with reads and writes. Okay, that's kind of the first 2 points there, is to be able to do high throughput and low latency. The other interesting thing, which part of it is from the database background that I have, but also Brian's a big believer in this, is to make sure applications are easy to write. So we wanted to focus on consistency in the database. Those of you who follow this field, I don't know if you've looked at the standard paper from Google recently. And it looks like the people who used to believe in NoSQL are also coming over to this. And I'm actually pretty proud that when we started this company as a NoSQL company, we said consistency was important. We had a paper at VLDB last year talking about ACID on then called Citrus Leaf, and our company name changed to Aerospike recently. So anyway, so that's the first 3 points there. The other 3, which is I think equally important, if not even more so for our customers, is the operational aspects of things. And it's very interesting to know that the various kinds of things that one wants to do, like long-running tasks, right? I mean, typically if you have a database which is running 24/7, people want to write these management tools, lifecycle management tools. They want to scan the database, clean up objects, expire them, take backups. All of those things need to happen, in our opinion, online. So there's no need to do that during low load time, if you will. We want to have the ability, and this is one of the reasons I wish, this whole million transactions per second, who uses a million transactions per node? Well, you don't actually need it. You need the extra capacity so you can do a lot of online things. Long transactions, data migrations when you add nodes. So you need a lot of capacity for that. So it's important to allow long-running tasks while not slowing down the SLAs of short transactions. That's a key kind of design goal. And it's a challenge too, to do that. Because it's particularly hard to do, as people have found out. Scaling linearly, I talked about. There are techniques we use in order to make sure that as you add nodes, we don't actually create more bottlenecks in the system. And as you add more client load, you're able to generate more throughput, provided you have enough capacity on the server side by adding nodes, for example. And of course, you need to be able to add the capacity with no service interruption. In fact, the time you want to add the capacity is the time you make sure. The last thing you want is to be in a situation where you need more capacity and you add a node and then essentially you lose the capacity because something bad happened. So these are all kind of fundamental challenges to these systems. And it's to a lot of systems, not just to us. A little bit about how our clustering works. This is a high-level picture to kind of introduce some concepts. The first concept, is that we actually treat clustering as a single data center problem. What that means is our clusters are tightly coupled. So we can therefore make certain assumptions of how close nodes are, how fast the heartbeat will be between nodes. So we can run a very fast heartbeat detection algorithm. We can make our Paxos algorithm terminate in a short amount of time. What you saw there, when I removed the node out of the cluster and the transactions coming back up, is basically the time it takes. It takes about 100 milliseconds or so for the clients to detect what is going on and readjust. And that's very important. And how do we do that? And the other thing we also wanted to worry about, we really were concerned about, was the complexity of the operational aspects of things. So we made a decision that we will have exactly one kind of cluster node, which means all of the abilities of all of the functionality that is needed in order to run the system, long-running tasks, queries, transactions, read-write transactions, backups, all will be shared by every node in the cluster. So our cluster is fairly unique, I think, in that you can have one node, two nodes, three nodes, and it's completely linear in terms of, and then it creates a bunch of issues you have to solve to make this. So our code is particularly hard in some sense, but actually it makes the operational stuff easy. The way we chose it is to make it a shared nothing system, so we're able to always do a rolling upgrade. That's the other thing we kind of guarantee you this kind of architecture. The other aspect of it is now that we have tightly coupled cluster within one, typically it's installed in the same DRAM or so. We can do an asynchronous, I would say, shipping to clusters which are in different data centers. So this is the way we kind of solve the entire availability problem. So that's the high-level picture there.
Usually, how much time does it take to replicate between data centers?
Typically, the lag we see is under a second. If you have a good, so it's constantly happening. So if you, for example, your connection to the second data center is cut for half an hour, you fall behind, then you can catch up. There are cases, if you're down for long enough, then it takes a long time to catch up, so you take a complete backup from one and restore it to the other. But assuming it's a well-running system, and you have enough capacity in the bandwidth and so on, the lag is well under a second, 24%.
Okay, but that depends on the bandwidth.
Yes, and typically people tune that. Our customers have to kind of plan for it, tune it, make sure that links are up, they have enough capacity and so on. Yes?
So where is the redundancy managed with respect to the load balancing? The customers will go only to one data center or all data centers?
It depends on how the customer wants to actually write their applications.
They have an option to replicate everything?
No. There are two aspects of things. First is, within a cluster, that is replication. It gives a certain level of redundancy. So within a data center, a node goes down, everything. It's kind of a tightly coupled, solid system.
Fine.
Across data centers, the optimization we have made is not for each request to go randomly or arbitrarily to data centers at the same time. In order to maintain consistency when you do that, one request could go to, let's say, a data center in New York, another one to one in San Jose. What will happen is, you need to therefore increase, and this is actually the standard paper, there's a whole bunch of things, how they optimize this, but the point is, you can't have a sub-millisecond response time for that. Because if you want the consistency on the next request, you'll have to slow things down a little bit. But we don't do that. So our customers slice and dice the problem slightly differently. But most of the applications we have seen, is the case where an application is geographically local in its access most of the time. When there's a failure, they can throw the switch. So the lag is, that's kind of how this is optimized for.
But that is only if you have an active passive data center. If you have two lifeline, then
We have two active for sure. The thing is, the same data item may not be actually in access in real-time code. So you could have the West Coast data and the East Coast data both in both data centers, but predominantly the actual data items accessed in the West Coast are actually West Coast and the other ones in the East Coast. That still works.
okay, but if it's in the ad serving system, you have impression counts for the same kind of
Correct.
So the impression counts would kind of differ by certain.
Well, the way you do that is we can detect conflicts. If you actually update the same data item in both, we can. Impression counts is actually a tricky problem because what you're talking about is actually a counter. A counter is hard to detect conflicts then because then I don't know what the right conflict detection is. We have abilities to do user-defined ways of detecting, resolving them. It's possible. Oops. A little bit about our hash table. Okay, one of the key things I talked about earlier is the importance of Aerospike in avoiding hotspots. Okay. So we spent a bunch of time thinking through the hotspot problem and pretty much avoiding it. That's one reason we can actually have 30-node clusters. We can take down any node at any point in time, add another, upgrade it, add another node. This is something our customers do constantly. And upgrading an Aerospike cluster is not something people are afraid about. And that's, I think, another thing we have kind of made sure of by the way we do the calling and so on. So the hashing algorithm is very simple. We use the RIPE-MD 160 hash function, which is a pretty robust hash function, to create what is called a digest. Now, given a digest, what we end up doing is figuring out, we kind of partition the key space, if you will, to about 4K partitions. And which means that given a key, it is very easy to, it's pretty much a static way of figuring out what the partition ID is. Now, the hard part is the dynamic part. So now that you have, like, let's say, a 3-node cluster, where are all these partitions? And how many masters you have, replica you have? We typically, all our deployments are going on with replication factor 2, as we call it, which means there's one master and one replica for each partition. But it's general algorithm. You can do three copies, you can do n copies where you have a copy in each node and so on. But pretty much all our customers use 2 copies because that seems to be fine in practice. Now, yeah. Well, the thing is, it is only 2 replicas, which means it's exactly the same replica. So the way the reads and writes differ is by the read can go to either replica. The write always goes to the master partition, which coordinates the write across both replicas. So that's kind of the consistency part. So whenever you have 2 copies, when you ask the question about ACID, we actually do single record transactions in production today, but we have to still coordinate the writes across these 2 copies. And when a node fails, there's a whole repeatable read scenario which you can, many of our customers actually relax to get better. It's a standard cap theorem formulation of, getting more availability by a little bit weaker consistency under failure situations. And because of the tightly coupled cluster concept, we are able to really focus the failure situation and make it as minimal as possible. So if an application can deal with data which is maybe an hour old, it can get a slightly earlier value only when these stressful events are happening. The alternative would be to turn repeatable read on in our system, which means we have to go, if you have 2 copies of the data, you have to go resolve before you return the read. And that's something which, you can choose it in our system. I think the question is,
do you have to specify in your cluster that one of the nodes is the master node?
No. We actually do all of this automatically using your Praxis algorithm. I can go into a little bit of the next one. The key thing here to know is there is a dynamic map of where the partitions go into a current cluster. When a new cluster is configured, which means that either the node goes away or a new node joins, then it's a new cluster. And then what was there before is known. What is there after? What should be there after is also known. And then there is a whole process which starts in a cluster, which is a real-time prioritization of the data rebalancing happening at the same time as read and write transactions. So that's kind of most of our IPs in that area. Okay. A little bit about how the cluster is organized. Once, you can actually bring up like several nodes and form an Aerospike cluster at the same time. You can pick up all at the same time. The zero config way of doing it is by using multicast configuration. So everybody's listening on the same multicast IP board. They're coming up, they see these gossip packets around, discover each other, and just form clusters. That's where the Paxos algorithm comes in. Again, because of the fact that the heartbeats are so fast, we can make the thing terminate fast. That's the key thing. And therefore, the cluster is constituted very fast. Once it's constituted, there's some, we can immediately start scheduling the data rebalancing. I think our goal is to get this whole vote, the Paxos voting and consensus and terminating it within 100 milliseconds. Which is kind of, again, the demo showed that you shut down the cluster node, you saw that everything kind of stabilized virtually. So that's the idea.
Excuse me?
Yes.
So 100 milliseconds is the time interval in which the Paxos algorithm runs to see the state of the node, state of the entire cluster.
Yes.
So, as per your experience, at what point or at how many nodes does it seem to deteriorate? And does that number seem to go back 100 milliseconds?
We've run up to 100 node clusters. It's fine. But I think there are some issues with running it to 1,000 node clusters, for example. Okay, I can see it. So we will fix it. But the other thing is we can do so much with one node. Typically 10x or something what other products do. So our small cluster sizes are extremely powerful. That's kind of the other, yes, and we do have to scale, and we have plans to scale beyond 500 nodes and so on, but that will, it's probably beyond the scope of this presentation to go into that.
The data replication, is it dependent on the size of the
depend on the partition. So we take the key space, we split it into partitions, and then each partition is replicated. So that's how we slice and dice it. So there's a fixed number of partitions in the system, pre-configured, 4K, and then we can also do 8K. I mean, the point is, and then there needs to be a way to change it from 4K to 8K. I think that's something we have not done so far.
So if an item packs inside 4K, then it's better.
Not item. The item can be whatever size you want. I'm talking about the number of partitions in the key space. It is not the size of the data. Typically, the sweet spot of data sizes are between 1 and 10 kilobytes. There are some issues with reading and writing at such high throughput on 1 gigabit Ethernet networks. So as you go to larger data sizes, you want to have a 10 gigabit network, for example. There are other issues which come into play. So we go at network speed, basically. So when you add a new node to a cluster which has come together, I kind of talked about a little bit, but it's kind of worth spending some time on this. The Paxos algorithm determines the new cluster size. The partition migration is scheduled immediately. However, we kind of throttle these migrations because these are essentially transferring entire partitions across. So it is possible, if you go at a high enough rate, you could saturate the network between the cluster nodes, and so nothing else will happen. So there's a whole real-time prioritization, and individual nodes can decide to refuse a partition migration, to initiate it with multiple threads versus one thread versus 4 threads. So we have ways of kind of controlling this. A lot of this is about figuring out how to manage these things in real time. And again, there are some tricks to making sure the partition moves atomically, because it's possible that you have a partition in one node just to move somewhere else, but the reads and writes have to continue to happen on the original node until the migration actually completes. And there is a time in that migration process where we open a write journal so that the writes are sent to both of these nodes, and then at some point this thing kind of fades away, and then that takes over. And that actually happens instantaneously, but it takes a lot of these gymnastics to get that right, because you can so long as you're running into both nodes, you can switch it over, and then you can shut this down. So we take care of the atomic switch.
Just to clarify, partition is a replica or actually one extra shard?
There is partition is simply a segment of the key space. So if you have a key space with like 1 billion, 3 billion, whatever entries in the actual database, and we have like 3 billion record databases. So you divide it by 4,000, 4K. That is the number of partitions. Each of those partitions, because of the RIPE-MD 160 hash function, pretty much has balanced amount of data. Okay, the robust hash function gives you the property. It's not our hash function; it's invented, I believe, in Europe. So, but it's a very robust, well understood. People have written papers on this, on the collision resistance, collision avoidance of RIPE-MD 160, and so on. Yes.
What's the reason for the 4K partitions only?
There is no specific reason. We did our calculation 2.5 years ago, and that actually has worked very well so far. I think we have to move to 8K going forward as we grow our cluster data sizes and so on. And I mean, to me, it's just a setting which at that point it makes sense, and it's worked very well so far. But there's no hard cost to it. And going larger, as we get, let's say, 1,000 or cluster, we probably want to have 16,000 partitions. Or more. There's nothing in the system which is inherently against that. And then through all of this stuff, transactions continue. That's important. How do you write data safely? Talk a little bit about this. All writes go to the master partition for that data. If there's a key, figure out the partition, send it to the master partition, and then that partition will, that node will coordinate the write to the replica. Returns back to the client only after both writes are completed. We do not actually wait until the disk commit happens. We wait until the data is written to memory and wrote, and then this stuff is scheduled. So that's a latency issue, and frankly, we've done the math on it, and it's a fairly rare case where that will fail. It's very, very unlikely, really unlikely. And this is actually an interesting thing that was discovered over the years. Replication versus persistence. kind of equivalent at some level in terms of the level of reliability. Scalability. I talked about scalability is really important. One important way to scale, which we have in Aerospike, is to make the client layer intelligent. So clients actually share what is called a partition map, so as to which partition is in which node. So given in steady state, in an Aerospike cluster, when everything, there's no migrations, no partitions are being rebalanced, every client has pretty much the partition map. So given a key, the client can determine which node to go to in the cluster. So completely, basically scale linearly. And there is no level of indirection in the cluster, even though we support a proxy protocol. In case during these times when a cluster is changing, it is possible that the client, because the client is only going there once a second to get the partition map. We do, 500,000 transactions a second, so that we have a huge number of transactions in 1 second if you have the wrong node. But we are able to go in an internal proxy protocol. Again, the philosophy is to make the client, the application simpler, which means that we make sure that the cluster will do the work. So there is no redirect going to the client. So we go find the data. The cluster always can find the data. Cross data center is the other thing. I kind of hinted about it in the first slide I had, but I'd just like to go through a little bit of a scenario here. So this is a scenario with 4 data centers. This is actually happened also aligns with the first deployment we made about a year ago on cross data center. The top cluster is in Amsterdam. The middle one is in Ohio. The one on the left is San Jose. The one on the right below is Texas. So what the customer actually did was set up a 4-way ring for some amount of data, which was globally shared across all data centers. Now, they also had all the US data. They wanted pretty much what we call master. Everybody is master. They wanted it replicated across all 3 US data centers, and that's the green kind of arrows you see. So the blue arrows are the global ones, the green ones are the US. The European ones in Amsterdam, they also backed it up in Ohio. And the reason they did that was, first of all, they needed a backup for DCP in case that thing failed. But also, they had this whole Hadoop kind of process they were running, which they would then feed into the real-time database. And their Hadoop process was running in Ohio, because you just feed it in locally. And then that would simply ship the data over, the changes over to Amsterdam, and they're pretty much caught up. So the idea of this is to make sure that you can manage a global big data system, so to speak, which each of these individual clusters are high performance with low latency. This is kind of how we decided to solve this. There are other ways to solve this, but this has been pretty stable, and we're talking to one of them today, who deployed with us 2.5 years ago when we did not have the cross data center support, built their own pieces, are actually actively considering moving to our solution here, which is kind of interesting, because this is not something, I've run services at Yahoo and so on, and I'm not very, it's not easy to convince me at that time to move stuff which is working. But there are 2 big advantages to doing certain kinds of shipping using our database, because the whole bunch of infrastructure people build, which is one-off, to do these things. And then even people who have done it for 2 years are quite ready to give it up for the right kind of solution. Yes?
So for the data center in US, it's like the architect is one.
It's a ring. It's a ring. They decided to do it as a ring. And all of it's going to go to here and to here, and then it's just a ring. So they're all in a ring. Pardon? That's a great question. If this one fails, then this application will not happen. So we have a star schema, which one of our newer customers is using. So you could do one master and a bunch of things. You could do star also. That way, you're then the center of the star fails. I don't know what happens. So there are choices you have to make. We support these various ways of doing it, but it's also not a good idea to make everybody go everywhere. I mean, that's like I don't know what it is. I don't know if it's a star. It's not a star. It's something. It's a mesh. Yes, exactly. Yeah, that's correct. Nice. And we do have, by the way, I forgot about the mesh. I talked about the multicast protocol for our heartbeat, discovery. We also have a mesh protocol So we run on Amazon, for example, quite fine, because we don't have multicast there. So our basic aim is to run wherever you can run Linux or commodity hardware. We will run them. All of this is software. It's agnostic to the hardware.
Sorry, can you repeat that? So if you don't have multicast capabilities, you use the
No, we use mesh which means that we do two-way network across all these nodes. So we are able to run on Amazon, for example. So when you bring a cluster up, it needs to find out where its cohorts are. Multicast gives a very simple way of learning, listening on one thing, zero configuration.
Yeah, but if you have a network that doesn't support that,
Then you do what's called mesh, which means that you have to tell each server where potentially the existing cluster is. To give you an idea, right, this is kind of this actually happened for us. So we were actually, this is like 2.5 years ago, when we were trying to demo this to people. So, and we couldn't possibly get people to use it in data centers. So what we did was we actually used Twitter as our multicast. So all our servers in this time used to tweet from Amazon. So you go to Amazon, just go click and say started, and then it will just join and say cluster. That's just a demo. This was like 3 years ago. And then of course, we deployed and now it's gone. Yes, that problem exists if you don't have multicast. So we do a whole bunch of things on. We're big time into performance and of all types. Brian's into it, somewhat into it, but Russ, it kind of lives and breathes it from Alchemy. So he's written a blog about how to get 1 million transactions per second on $5,000 of hardware. So feel free to check it out. And a lot of tricks there. And you can use it also, those tricks for anything that you're doing if you really want to tweak your system. But most of our customers don't need to do it because we don't run at that level of capacity. Because we want a proper cushion in your ops. We spend a lot of time optimizing SSDs. And we figure out how SSDs work, and there are SSDs which work well for database kind of workloads, others which don't. So we've written a tool which essentially you can run to certify SSDs. We can predict, and we have predicted future failure of SSDs based on how they perform in our tests. Some of our customers have chosen not to actually use those recommendations because of whatever reasons they have, but eventually we actually have run into those. So we have a fairly good set of optimizations for SSDs that we do. And this is actually critical for some of for most of our deployments in some sense, because of one reason. The technical details are interesting, but here is the real kind of killer here. You actually get, SSDs are so much cheaper per bit to store than main memory is. And we can, with the way we do our algorithms, with our main memory having the index, we put an index for each object. We have probably the smallest index structure per object, that we know of. What that allows you to do is to be able to kind of ride the cost curve of SSDs. So you say many of our customers just look at this, we have a sizing spreadsheet. If you really are deploying these things, you could potentially start with a simple main memory system and then switch over to SSDs as your data sizes become larger. It's a slam dunk, basically. This whole thing was calculated by one of our customers in Japan. Pretty much a no-brainer for them. And that's critical. We're still doing millisecond response time. We probably can't do 100,000 transactions for SSDs. Typically comes to 10,000 or 20,000 for SSDs. The Amazon recently has an SSD instance we did release. We worked great on that. All of that actually works really well. And this is something we worked on for 3 years. We're fairly expert at it. So this is just a summary of what we do. I'm not going to read it. So essentially, I've talked about how we can do things fast, how we, I kind of hinted about how to scale, and the whole never failing thing is pretty much what we live with the company from day one. Okay. So a couple more things about Alchemy and how our company is moving forward. One of the things that Alchemy brings to the table, so far I've talked about the bottom kind of rectangle of the key value store aspects of the thing. This is the one thing that's deployed, worldwide, across all these dozens of customers and so on. 24/7, we worked on the shared nothing database, scaled it out, multiple data centers, BCP, optimized the storage layer. I didn't talk about the multi-core optimizations, but basically we kind of made this really tight and really good. What Russ did with Alchemy initially was he actually building the higher layers of what I would call the new database. Okay, we call ourselves a NoSQL database, but we're really a database, or real-time database is the way I think about this. Okay, we're just bringing new technologies and rebuilding the database. Now, what Alchemy did was they, Russ built several of these features on top of Redis as a platform. Okay, Redis is a great kind of single kind of node, whatever, it works fine. But we basically have extended this to something way beyond that. That's one main reason why Russ is now part of Aerospike. So working on, with the rest of our team on building some of these things. And if any of you actually have ideas here as to what makes sense and so on, feel free to kind of talk to Brian here, who's, and also me. This is something we are actively kind of soliciting input on and figure out where the industry should go.
You're trying to build a compute grid.
Pardon?
You're trying to build a compute grid on top of this.
I would not go that far.
I do.
Yeah.
I do.
Okay, so here we go.
This ends up being a compute grid at the same time.
Yeah,
so
can
the
be.
ability to run user-defined functions, we've chosen Lua as our implementation language for that, gives us the ability to really push the compute and the data closer together. It ends up being very close to a compute grid, but really a new style due to the low latency that's involved.
What did you say was the
Lua.
That's one of the languages we could use for stored procedures, and that's something.
Our first beta customers are using Lua for that due to its low latency.
But as is, it's just a key value lookup, right?
When you say is a key,
I'm like without the Alchemy part.
without the Alchemy part, this is a key value store. Platform which scales fast and so on. And that's why we're moving here. As you can see, we pretty much have done, we believe, a very good job of this, but we are kind of want to do more. I think that's pretty much my talk. So this is how, how can you get Aerospike? We have a community edition. You can download it and try it out. If you think that you need more than a community edition, talk to us. But basically, we're ready for deployment at short notice.
Okay, guys, before we move on to the Q&A, I just want to give a quick round of applause for our awesome speaker, Srini. As mentioned before, Beats by Dre headphones will be given away by email. Well, not by email, but you will find out how to enter the raffle by email. And we have a couple more prizes. Who's the first? You won't. There you go. All right. A couple more to go. Who's the next to raise their hand? Did you get one? Wait, I gotta give you a chance to that side of the room. Here, you get one.
I get one.
You got one. I can't throw these. One to here. All right, you really do one. Oh, sorry, that was a short shot. Swap it with me.
You gotta throw it.
Yeah. In the air. Cool. Who wants it? Cool. Last two. All right. Q&A. Okay. First question of the evening.
I'd like to have Brian join us.
Oh, did you want to give an intro? No. Introduce yourself.
Srini already told you about what I do. So we wrote this originally starting about 4 years ago. I'm Brian Polkowski, co-founder also with Srini.
Your question.
Yep. So referential integrity, was that a key design goal, right? And do you support, aside from NoSQL, right? Was it also a design goal to support one of the, you said SQL-oriented, concepts like, triggers or,
I'm going to...
Let me just repeat the question. Referential integrity, was that built from the start with, right?
Is that a design goal?
Was that a design goal?
Design goal.
Design goal, and built from the start to be part of the design, and also is any of the relational elements part of the design?
I'm going to answer the first part and then Brian add to it. Our design goal is to build a database for the new kinds of applications at high speed. Our design goal has not been to repeat what has been done before. Okay, we want to do it 100x better, not 10x. Most cloud catch up in 3 years. We want 100x better. So that's our design goal at some level. And now on the reference integrity part, we have basically stayed away. And Don Hatterley, one of our DB2 guys, one of our advisors, the chief architect of DB2, and he advises us on this one aspect. He says it is very easy to take a fast platform like what we have and make it slow. The trick is to add features so that in such a way and carefully, this is why we're spending some time taking the Alchemy work and actually massaging it in to the right use cases which our customers will use for big data. And none of them actually have given us an interest in reference integrity, for example. The list I put out there, the sub, for example, triggers I think is interesting. Yeah. But reference integrity itself, maybe you can add to it on the application level.
There's Roger Sipple, actually, the founder of Informix, gave us an interesting tip on this as well. We asked him, how long did you run Informix before anyone actually ran, before you introduced referential integrity? And he said 6 years and probably about $100 million in revenue. That was about 15 years ago. So we figure we have a little ways to go before doing referential integrity. The fact is, if you're sharding MySQL, you've already given up on referential integrity by and large. And most people run MySQL without referential integrity either. So, we think there's a long way to go before that. Another interesting thing is, being here in New York, I went and talked to the guys at Citibank who actually do all their XA transactions. They don't use the referential integrity in SQL. It's not good enough for banking.
They do it in the application layer.
They do it in the application layer, exactly. They have roll back and roll forward with transaction, what they call workflow. You have to debit one account, put the audit log for it, do the next one, do the next one. So banks don't need it, and the internet doesn't need it. So you can go a long way without referential.
But there's also a little, what I see as a slight shift going on. Because I've been in the database field for so long. Right? The initial thing was the data was king. Everything had to be done in the database, and the application, do whatever. We're not going to. Now I think we've moved a little bit more to where I see the new applications. They have give a little bit more control to the application. In fact, again, I go back to the Google's panel paper with the transaction. They actually talk about how applications pick and choose, and we do that too. Our applications pick and choose things, and I'm sure reference integrity will be important for some applications, but they have to give up some performance, some latency. If they're willing to give up those things, I'm sure we can support it. It is well understood. But those are the trade-offs, I think. And again, I agree with Brian in terms of the time when we would have to do it. Right now, not right now, for sure.
Next question? Yes, right there.
In your TCO slide example, you had, I think, the SSD has 3 servers versus 16, memory. I'm just wondering, are there any particular downsides to, running SSD versus the other scenario that's not obvious?
Yeah, it is
obvious.
Yeah.
Yes, there's a few. Are they obvious?
The thing is about running on SSDs is you can, and we have proved it in production. 2.5 years ago, it was a promise we made. Now I can talk about the promise we kept. But basically, we can actually run day in and day out at 500,000 transactions per second. Day in and day out with SSDs, with 1 to 2K objects going in and out with the optimizations that we've done. So it is actually possible. If you had to do that with memory, you would have to spend like $10 million for the machine or something, as opposed to whatever $1 million it costs to do those kinds of clusters. So it is possible to do that. But therefore, and there are problems. Okay? You asked about issues with SSDs. Typically, the SSDs are the things I talked about. Essentially, you run the SSD, run a 48-hour certification test, and then the thing actually doesn't pass it.
So here's what's non-obvious about SSDs. I'll be doing a blog post actually on this later this week. The read latency to SSDs depends on how hard you are writing to it. right? If you don't do reads and writes at the same time, you're not going to get the full characteristics of the drive. If you do a steady write load over the course of time, you end up basically getting garbage collection issues, right? So, and even what's really crazy about it is if you just leave the drive alone for 15 minutes, plugged in, it will unfragment itself under the covers. So it's very hard to do performance measurements on the read latency of these drives, given that you have to jam writes at it at the same time to really see what happens in a real-world scenario of a constant write load. So with all of that true, you can still find the drives that do garbage collection well and do it at a reasonable price. We recommend a lot of the Intel 320s right now. We're recommending a lot of the Samsungs, which was the Model 6000, the newer one. And we've also found in general that MLC drives are fine. And there's sort of two reasons for that. One is, if you have an architecture like us, hey, look, a drive fails, bring the server down. It's down for an hour. You slot some new drives in. You had 2 copies of the data. You bring it back up. It repopulates. Everything's fine. That's one of the benefits that we have. Essentially, you can think of it as server-based rate.
We have not actually found a lot of failures with SSDs. We've done with hundreds of them.
So, and here's the other non-obvious thing. MLC is fine because if you're writing faster than MLC can handle, probably what's going to happen is your read latency is going to go through the roof anyway. So a lot of the calculations we do, and Intel is very good about having correct monitors for this, the drives will last about 3 years if you were doing a fairly appropriate level of writes to it. Well, frankly, in 3 years, everything's going to change in SSDs anyway. We're probably going to double all of our capacity. So that's fine for most of our customers. We actually drive through with their particular write load how long it's going to take to burn out the drives. And right now, this scenario is very, very good for MLC. We also recommend a lot of OCZs. We have those in production, various different models. And we're doing some very innovative work with Fusion IO that I can talk about afterwards as well.
Okay, before we take the next question, anybody ask the audience one quick thing. Does anybody here want more database and beer together? Yes. Come on, that's pretty lame. Right. Tomorrow, thanks to Aerospike, tomorrow there is a drinks and data free event. Not data free. Free drinks and data event. It's tomorrow at 6:30 in Dewey's Flatiron, which is a bar on 210 Fifth Ave. So guys, if you find these cards around, it does tell you how to get more free beer and database stuff. Yes, all the way in the back there.
Since you brought it up, a lot of the SSDs performance really relies more on the controller than the actual memory itself. And so an OCZ drive set can vary tremendously, whether they're using SandForce or something else. I know this is related to this, but it's worse than that. What's that?
It's worse than that.
So I was going to, without diving, obviously this is a whole discussion in and of itself, but you guys seem to have really pushed out on the limits. I was wondering if you could speak to that for like 2 seconds, just because you've got
So let me put it to you this way. We had to build our own benchmark tool. It's available for all of you to run. That allows you to run a read and write load and actually see the read latency you're getting out of your drives. What we had to do with OCZ in particular was find drive models, what's called a locked bomb approach. Because even a particular model that has the same serial number, they will in fact use different chips. They'll have the same controller, but they'll have different underlying chips with different performance characteristics, which, given the promises we make to our customers, can be problematic. So that's one of the things we did was we said, look, let there be a tool, it's open source, it's freely downloadable, to allow you to measure your drives and see what characteristics they're going to have.
And that's on your website?
Absolutely.
That's great. Thanks.
Next question. Guy right there in the back.
How do you differentiate yourself from Cassandra?
They're slow.
And they're not consistent.
They're not
That's the main reason.
And do you like tuning Java VMs? If you really enjoy spending your time tuning Java VMs, Cassandra is the choice for you.
Next question? Yeah, right here.
So going back to infrastructure, you mentioned being able to do sizing very quickly.
Yes.
I don't know if you can elaborate on how you achieve that.
Well, it's basically because the way the product works. So we can size it to say, if you give me a certain set of certain drive, like OCZ, we know how many transactions per second we can do fine with it. The CPU is not an issue as much until the indexing stuff comes over. But right now, with the key value store, CPU is fine.
Based on
Yeah.
the size of the data?
The size of the data, how much data you have, and what's the size of the SSDs, and how many SSDs. It's important to actually have multiple SSDs per node, because we can then stripe across those SSDs the various data items, so we can give you 4x, whatever it is, 5x. Some customers, one customer runs with 21 SSDs per node, because they have very small SSDs, but they can get a huge amount of throughput from each node. And that's kind of where the sizing typically is. It's the size of the data which you can keep per node, and the throughput you can drive through per node. We can do a lot on both, and that gives you a double kind of performance impact there.
Another benefit is a core value that I had in developing this code was what I call worst case server design. So what you do is, instead of trying to make the best case go fast, you make the worst case prevalent, and then you make the worst case go fast. So the way the architecture works internally, we don't rely on caching to go fast. If you throw more DRAM, it doesn't go any faster. It always works at worst case performance. And worst case performance is very, very, very fast. So that allows us to say, walk into especially these advertising customers, you know what? The cache hit rate changes in November. Right? So you do all your measurements in June, and in November, what's your cache hit rate? I don't know. I know how much traffic is going to come in the front door, but I don't really know what my application design parameters, especially in terms of working set size are. I have no idea. So we say, look, it's not going to matter. The caching parameters don't matter, because we're always going to go do one IO, and we always keep all of the indexes in DRAM. Period. So there's no caching. You get the worst case equals the best case equals fast.
Right. It's about predictable performance.
How big is those indices?
One cache. Well, basically, the index is one cache line per object. So 64 bytes. Always 64. It's not one of the reasons why we use a memcache style RD tree, even though it's a little primitive as a data structure, is that B pluses and such have unpredictable memory size performance. Right? So while we're doing secondary indexes using B pluses, we should probably switch to T trees. That's a whole other argument. But the team doing that, I say, how much DRAM is it going to take? They say, well, it depends, and then the cardinality of the results, and it could be this and it could be that. Best case is 1, worst case is 7. And the nice thing about these primary key indexes is we can tell you the exact number. It's 64 bytes. It's never 67. There's no fragmentation effects. We don't use the standard allocator. We use a slab.
It's independent of the size of the
exactly
key.
what it is.
It's independent of the size of the key. So we can.
Hang on. Questions. Next question. There's one. I'm not making you feel bad. We have one-on-one with the speakers afterwards, so any involved questions, I might cut you guys off. Please don't get offended. It's just, got to have time for everybody. Next question.
On the how you evaluate compare against more DB as well, because they are also going to get into the same kind of space without.
We haven't actually played with it ourselves, frankly. Everyone knows that Starkey's a cool guy, and what he does is pretty interesting. But we haven't actually played with it ourselves, and I don't know what customers they have. NeoDB? No, they started when we did. They snaked us out of funding one of the VCs on the West Coast. We went
What's the question again?
The question was something about NeoDB?
Yeah, NoDB.
NuoDB.
NuoDB.
Oh, yeah, NuoDB. What was your question specific?
We haven't tried it.
Sorry. Yes, how do we compare? How does Aerospike
How do you compare to
NoDB?
Okay, so the answer here is we don't know, but it's not next week, it's the following week, but yeah, you can fire the reverse question.
Ask them how big their largest deployment is.
Okay.
I think they're still in beta, though. I'm not sure if they.
Yeah, they're beta, right?
Yeah, they started the same time we did, but we've been in deployment with, we're now up to a lot of very high scale.
Next question? Yes?
In terms of hardware, so you mentioned commodity, but do you have recommendations around? I guess is it like standard like standard 2? I guess 3 gig per second, SSDs or local drives or whatever.
Any recommended hardware configuration? That was the question.
We have a set of those, so we can share with you.
It tends to be light on the CPU. Most people buy more CPU than we tell them to. For some reason, everyone wants 8 cores, even though we say they only need 2. I don't know why they want to spend money on cores. Intel is very happy on this other DRAM speed doesn't really matter. The network matters, especially using multiple receive cores, multiple queues and transmit queues. That's key to performance. And the SSDs end up being a very large factor.
Basically, we work with standard data center hardware. The network card is very important.
Yeah, but if you get SSD and you can put it in CBAN, you're pretty much prepared and you also very serious.
We do everything over 1 gig. Most of our customers are running 1 gig or possibly bonded up to 2 or 4. We don't have any deployments as far as I know currently.
We do have one.
We do have one.
Last question of the evening? Yes?
How do you price your enterprise?
We price for the key value store by data. And I'm actually kind of passionate about this. This is the same model Vertica uses. So if you price by node, or like a lot of service-oriented companies and open source companies do, there's a natural tendency for ops people to use fewer nodes, which creates a more fragile system. You know, when you're out of hardware, you're out of hardware. There's no magic pixie dust we can sprinkle on it to make it better. So we want to decouple the ops choices of the number of machines from the business problem of how much data you're storing. So it's the number of terabytes in your cluster. I'm not going to tell you. I'm talking Gino, he's back there.
Yeah.
He'll make you a deal.
Yes.
Oh, okay. One more question. Yes.
You can have the
Put up his hand. All right, that's the end of our time. Srini will be here if you have any more questions. He'll be here for one-on-one questions. Thank you, everyone. Thank you for coming.